Okay, welcome back. This is on curve sketching. Okay. So we'll, combine all these ideas that we've been developing in Chapter 4, the first derivative, second derivative information, um, along with the um, horizontal asymptotes. We'll combine all that information to graph pretty much anything you can imagine. Okay, so 4.6 is a summary of curve sketching. And the way, the sort of how I want you to do it on a quiz or on the test um, is the following. I want you to identify the domain. The book wants you to get the symmetry. I'm not worried about that. Secondly, get the x and y-intercept and the vertical asymptotes. Thirdly, the horizontal asymptotes. Or the slant asymptotes if the horizontal ones don't exist. And then fourthly, do the first derivative and its number line. And identify any max and mins. And then fifthly, the second derivative and its number line. And so with the first derivative, you should have your test value signs conclusions. For the second derivative as well, test value signs conclusions, and then concavity. Okay, is the conclusion for the second derivative. Okay, what else do we need? Then 6, you're going to go to graphing this thing, and the graph is really dictated by these kind of number lines that we're generating. So you should have a number line for f of x, which we haven't been doing, but it'll tell you if the function is above or below the x-axis. Okay, so you'll be plotting zeros as well as undefined places. Then you'll have a number line for f prime of x, where you'll be plotting again where the derivative is equal to 0 or where the derivative is undefined. And then you'll have a number line for f double prime of x. Right? Okay, so now over top of it, then it'll force the graph to behave in a certain way. If you know this information, it forces this thing to be a certain. Okay, so let's go ahead and take a look at this process. And we'll start with a rational function, number 3. F of x is x squared all over x squared plus 3. Okay. So first off, get the domain. So for a rational function, the domain is all real numbers except where the denominator is equal to 0. And in our case, the denominator is never equal to 0. So x squared, if you set it equal to 0 and try to solve, there's no real solutions. Okay? So the domain is all real numbers. Okay. Secondly, then get your x-intercepts, y-intercepts, and vertical asymptotes. So for the x-intercept, you let y equal 0. And it just comes down to setting the numerator equal to 0. Literally, you're solving this, but in your first step, you're multiplying both sides by x squared plus 3. And so you're just finding where x squared is 0. And for us, that's just at 0. So the x-intercept 0, 0. Get your y-intercepts. That's where x is equal to 0. So y is 0 all over 0 plus 3, which is 0. And then the asymptotes, that's where the denominator is equal to 0. So there is no vertical asymptote. Okay. So horizontal asymptotes and the slant asymptotes then. So here the numerator and denominator have the same degree. So you expect horizontal asymptote. In particular, you take the limit of this thing as x goes to infinity, and then as x goes to negative infinity. Of course, in this case, they'll both be the same. Okay, so this limit is the same as the limit as x goes to infinity of x squared over x squared, which is the same as 1. So 1, this limit is the same. It's the limit as x goes to negative infinity of x squared over x squared, which again is the limit of 1, which will be just 1. So the horizontal asymptote HA is y equals 1. So now we're going to worry about the first and second derivatives and the corresponding number lines. So f prime of x is low d high minus high d low. So low x squared plus 3 times d high is 2x minus high is x squared times the derivative of the low is 2x all over the low squared. Okay. So this will be then 2x cubed plus 6x minus 2x cubed all over x squared plus 3 squared. The 2x cubed seem to add away. And we got 6x all over x squared plus 3 squared. Okay, we're going to need the places where this thing is undefined and equal to 0. So 6x, you take the numerator, set it equal to 0, so that'll happen when x is 0. The denominator will never equal 0 again. So our only real number of interest will be x equals 0. So we'll plot that onto our derivative number line once we get there. 5 then, the second derivative. Again, we go low d high minus high d low. So low d high is x squared plus 3 squared times 6x. Low d high, so it's just 6, sorry. Minus high d low, so 6x times 2 times x squared plus 3 times 2x all over x squared plus 3 squared to the squared, so it'll be x squared plus 3 to the 4th now. I can factor out an x squared plus 3 squared, so this will be x, well, just x squared plus 3, not squared. The leftover bit's 6 times x squared plus 3 minus what's left here. We have a 6x times 2 times 2x, so 24x's. Be very careful. All over x squared plus 3 to the 4th. Then you can remove one factor of x squared plus 3, and we get 6x squared minus 24x plus 18 all over x squared plus 3 to the 4th. I need to find where the second derivative is, and I think I made a mistake back there. Let me see. Oh, this should be x squared, sorry. So, sorry about that. That'll mess things up just a little bit. 6x squared minus 24x squared is negative 18x squared plus 18 all over x squared plus 3. Okay. Now I need to find where the second derivative is undefined or equal to 0, because I'll be plugging those on my number line for the second derivative. So set the numerator equal to 0. 18x squared plus 18 is 0. Solve that equation. Negative 18x squared is negative 18. So x squared is 1, so x is plus or minus 1. The denominator is never equal to 0. So x squared plus 3 for the same reason back here that it was never equal to 0. Okay, so we got all of our information that we need. Now we need to set up our graph and label, put number lines underneath and label those. This is f of x. This will be f prime of x. And then below that, we'll put f double prime of x. Okay, you want to connect all these number lines to the original graph because these are going to dictate the behavior of that graph. Okay, so first off, for f of x, what are you plotting? You're plotting zeros and the places where it's undefined. Zeros. And when I say zeros, I don't necessarily mean 0, except in this case it will be 0. When I'm asking for our x-intercepts. So let's put x-intercept instead. X-ints and undefined places. So the x-intercepts from above, we have 1 at 0, 0, right? So all I have is 1 in there. There's no undefined places. In other words, there's no asymptotes. So I'm not worried about that. Okay, go on. F prime of x, we have 1 critical value at x equals 0. And then for the second derivative, I had 2 potential inflection points, 1 at -1, 1 at +1. So -1, +1. Okay. So now for each, I kind of have to do test values, signs, and conclusions. So these problems are a lot of work. I still remember from 20 years ago doing these problems. It's ridiculous how annoying they were to me back then. You do enough of them, it'll drive you nuts. But anyways, let's go ahead and start with this. The test values, I'll just try -1 and 1. I'm plugging these into f of x. So these statements over here remind you where to plug in your test values. So if I plug -1 into f of x, I'll get -1 squared is positive over a -1 squared again, positive plus positive is positive, positive over positive, it's positive. My conclusion then is it's above the x-axis. So it's fooling around up here somewhere. I don't know what it's doing. And this interval then, if I also put in 1, 1 squared is 1, 1 squared plus 3 is positive, positive over positive is positive. So again, it's above. And it must just be coming down and then touching the x-axis and then going back up. Okay. Let's make sure about all this. So again, I got test values x is 1 and -1. Using now the first derivative, plugging in -1, I get a negative all over a positive. If I square anything, it'll be positive. So the bottom is always going to be positive. So it's negative over a positive is negative. So in the first interval, it's negative, and that means it's decreasing. If I plug in 1, I'll get a positive over a positive, which is positive, which means it's increasing. Likewise then, because of the first derivative test, I have a minimum value at x equals 0. So I'll just note that below, relative min at 0, 0. Finally, then we work with the second derivative, which is right here in my notes, and get some test values to plug in. Okay. So if I plug in -2 into here, I'll have a negative times 4, which is negative something bigger than 18. So this plus this will be negative. The denominator is always going to be positive. So negative over a positive, that's telling me it's negative, and so it's concave down. If I plug in 0, I'll get a positive over a positive this time, so that would be positive concave up. If I plug in 2, I get negative 18 times 4, which is something big negative, plus something smaller negative is something negative. Negative over something positive is, again, negative, so I'll have concave down. Okay, the second derivative test also then will tell us there's a min at 0. Remember, if the first derivative has a critical point in an interval such that the second derivative is concave up. This point will be a minimum value. Okay. Okay, last but not least, we compile all this information and produce our graph. Okay, so let's do that. Is there anything else? I'm looking for my, okay. So there is a horizontal asymptote at y equals 1, so let's label that. It has, let's label the x and y intercepts. There's just one at 0, 0. There are no vertical asymptotes. Okay. And so it's going concave down, and then it'll have like an S shape where it hits the inflection point at -1. And in this direction, it's getting really, really close to 1. So it's concave down, and then it has an inflection point where it goes concave up. It hits 0, and then in this direction, it'll be concave up until it hits that inflection point, at which time it'll become concave down, and it'll go in that direction. Okay, so it'll look something like that. Notice everything fits. I'm above the x-axis. I'm decreasing in this interval, and then I'm still above and increasing. It's concave, so shape downward, and then it goes concave upward, and then go back concave downward again. And the horizontal asymptote is at y equals 1. So you've graphed your first kind of non-rational function in a very rigorous way. All right, so let's kick back and do another one. And then we'll look at maybe graphing a logistic equation. Okay, so this is problem number 9. We have y equals x squared minus 6x plus 12 all over x minus 4. And we just have to go through the same process. So first, the domain will be all real numbers except you have division by 0, or you have radicals, or something of that nature. And here we have the potential for division by 0, so we need to look at that, whereas x minus 4 equals 0. So the domain will be all real numbers except 4. So the domain is -infinity to 4, union with 4 to infinity. Okay, so we'll have a vertical asymptote right there at 4. So right, the x-intercept is where y is 0, so have 0 is x squared minus 6x plus 12 all over x minus 4. In other words, just set the numerator equal to 0. X squared minus 6x plus 12 is 0. So it looks like, well, I don't know. I can't factor that thing. The discriminant, though, the innards of the radical part of your quadratic formula is going to be, well, let's look at it. So b squared minus 4ac. Okay? 36 minus 4 times 1 times 12 is definitely less than 0. So what I'm getting at is there is no x-intercept. Solving this would result in imaginary solutions, so there is no x-intercept. The y-intercept, then, you get that by letting x equals 0, so y equals 12 over -4. There is one of those. It's at 0, -3. Okay. And then the vertical asymptotes, we kind of already have that, right? That's where the denominator is equal to 0. And that's where x is 4. Okay, so there's that. Secondly, then, we want to know the end behavior. Okay, so the horizontal asymptotes, right? HA. If you take the limit of this thing as x goes to infinity, what do you have? X squared minus 6x plus 12 all over x minus 4. That's equivalent to the limit of x squared over x as x goes to infinity, which will be the limit of x as x goes to infinity, which means it's going to positive infinity. So there's really no horizontal asymptote there. Let's look the other direction. X going to negative infinity of x squared minus 6x plus 12 over x minus 4. In that case, you're looking at the limit as x goes to negative infinity of x. Okay, so as x goes in this direction, y equals x will go to negative infinity. Okay, so in that direction goes to negative infinity. So there really isn't a horizontal asymptote, but there will be a slant asymptote. So when this happens, you look for the slant asymptote. And to find the slant asymptote, you have to do long division. Okay, so for long division, you're going x squared minus 6x plus 12 divided by x minus 4. So you're thinking, what times x is x squared? Well, x. So you get x squared minus 4x. Subtract that business. So you get negative 6x plus 4x is negative 2x. Bring down the 12. And then what times x is negative 2x? Well, that's minus 2. So I get negative 2x plus 8. Subtract away. 12 minus 8 is 4, and that'll do it. Your slant asymptote is this portion right here. It's basically what you're doing is taking the limit of x minus 2 plus 4 all over x minus 4 as x goes to infinity. And in that case, this part is going to go to 0 really quick, and you're kind of just left with approaching this line here. Okay, so it's not really a limit, but what it comes down to is just take this part right here, and that'll be your slant asymptote. Okay? So I shouldn't have said it's a limit, but we get the idea that its end behavior is this line from the limit. So if you take the limit of this as x goes to infinity, this part will go to 0 because you have 4 over some variable expression that's getting bigger and bigger and bigger. So 4 over 10, 4 over 100, 4 over a million, that'll go to 0. Okay, and it just sort of leaves this portion, so x minus 2. Anyways, there's that. We need the first and second derivatives. So we're going to have to use a quotient rule. So f prime of x is low d high minus high times the derivative of the low. Derivative of the low is just 1. All over the low squared. Okay, clean that up a little bit. So we got 2x squared minus 8x minus 6x is minus 14x, and then plus 24 minus x squared plus 6x minus 12 all over x minus 4 squared. Okay. Clean that baloney up. 2x squared minus x squared is x squared. And then minus 14x plus 6x, I believe, gets us back to 8x. And then 24 minus 12 gets us to 12. Okay, so I need my critical numbers or critical values. So set the numerator equal to 0 to find where it's equal to 0. Looks like 2 critical numbers, 2 and 4. And then also set the denominator equal to 0, because that's where the second derivative will be undefined. Technically, it's not a critical value, though, because the original function is also not going to be defined there. So it just means it's not going to have a max or a min there, because the thing has an asymptote. It has a vertical asymptote there. But we still include it on our number line because the slope can change over that frontier. So you may have a vertical asymptote where it's decreasing and then it starts increasing on the other side. So you still consider it on your number line even though it's not a critical value. Okay. Fourthly, then, I'm going to get the second derivative of this character. So low d high minus high d low. The derivative of the low is 2 times x minus 4 to the first power. You can factor out a factor of x minus 4. Of course, in the denominator right now, we're at x minus 4 to the fourth. But up here I have, well, there's more than one x minus 4, right? So if you look at this derivative, it's actually 2 times x minus 4. So there's going to be 1, 2, 3 x minus 4s here, and then 1 x minus 4 over here. But actually 2 x minus 4s, because we could factor this, right? So let me rewrite it. I'll have 2 times x minus 4 cubed minus, and then there's going to be 2 x minus 4s here. So 2 times x minus 4 squared times x minus 2, using this factorization to help. Okay, so it looks like a mess, but there's stuff you can do to make it easier. Factor out then the 2x minus 4s. Okay. So I'll have x minus 4, and also the factor of 2. Let's do that as well. Then I'll have left over 1x minus 4 there, and then minus 2 times x minus 2, which should be minus 2x plus 4, right? And then all over x minus 4 to the fourth. 2 factors will cancel out with the denominator, and I'm left with 2 times x minus 2x is negative x, and then 4 minus 4 is just 0, so it looks like negative x all over x minus 4 squared, assuming I didn't make any silly mistakes, which I probably did somewhere along the way. Yeah, I did somewhere. Yeah, no, that was too good to be true. Sort of looking around for what I screwed up. Oh, it's x minus 6x minus. So there's not 2 of them there. That's what's screwed up. There's an x minus 4 here. Oh yeah, there are 2. Then there's an x minus 4 here. So there would be x minus 4 squared. But then this guy isn't x. It's back here is where I screwed up. Way back here. Geez. It's actually x minus 6 and x minus 2. Okay, so our critical value 6 and 2, and then dumping back down here, I really won't have that extra x minus 4, right? It's just x minus 4 times x minus 2 times x minus 6. Crap. Okay. So if you can only factor out one of the x minus 4s, then this thing will be squared. Ah, crud. Frickin' A. All right, so let me try that again. The second derivative of x, I have low d high, so x minus 4 squared times the derivative of the high is 2x minus 8 minus high d low. So I'll have x squared minus 8x plus 12 times 2 times x minus 4 all over x minus 4 to the fourth. You can factor out an x minus 4. Way too optimistic in my last factorization. You have x minus 4 times 2x minus 8 minus 2 times x squared minus 8x plus 12 all over x minus 4 to the fourth. Then we can remove one of those factors and FOIL out this stuff, distribute this stuff. So I'd have 2x squared minus 8x would be minus 16x plus 24 minus 2x squared plus 16x minus 24 all over x minus 4 to the third. Okay. Then what? Well, the 2x squares cancel, the 16x's cancel. Wait a second, the whole numerator cancels now. So I made another mistake somewhere. This is turning into a nightmare, isn't it? So what was the deal here? I have 2x squared minus 8x is minus 16x plus 32. 8 times 4 is 32. I apologize. So positive 32, I guess, minus 24 is 8. Oy, and that's it. 8 over x minus 4 cubed. Okay. So I need the potential inflection points from this thing. The numerator is never equal to 0, so no help there. The second derivative is undefined, where this thing is equal to 0. In other words, where x minus 4 is equal to 0. In other words, where x is equal to 4. But again, that won't be an inflection point in the technical sense because this original function is not defined at 4. But we still include it on our number line when we go to our final graph. So let's take all this information and go at it. All right. Okay, so this time I'm going to use the whole page. And here's my number lines below it. So I'm going to label my number lines f of x, f prime of x, f double prime of x. On my graph, I'll note there is a vertical asymptote at 4, 2, 3, 4. 2, 3, 4. What else? There's a y-intercept at 0, negative 3. 3 there. As far as my f of x goes, I'm plotting, again, x-intercepts and undefined places. So the x, there was no x-intercept, but there is an undefined place here at 4. So maybe put up an empty dot there instead of a closed dot to remind yourself. What else then? F prime, its critical numbers at 6 and 2. And then it was also, we have to include these places where it's not defined. So at 4. And that'll carry on to the second derivative. We also have to include that there. The second derivative, I don't think, did we get any critical numbers? No. Or any, sorry, inflection point numbers? No, we did not. We just have the single one at 4. Okie dokie. So we need our, again, our test values, our signs and conclusions on each interval. Okay, so for the actual function itself, let's pick x equals 0 and then x equals, I don't know, 6. At x equals 0, we already know it's negative, right? It's because the y-intercept is negative 3. So it'll be negative, it's below. The actual graph is below the x-axis. At 6, if I put that into the original function, wherever that is, if you put 6 in here, it'll be 36 minus 36 is 0, plus 12 is positive, 6 minus 4 is positive, positive over positive, it's positive. So in that interval, it goes above the x-axis. For this, then, let's try x is 0 again, and then x is 3, and then x is 5, and then x is 7. And this time we're using the first derivative, which is sitting right here, this guy. We could rewrite the numerator as x minus 6 times x minus 2 all over x minus 4 squared. Whatever we put in the denominator is going to automatically be positive because we're squaring it. So I need only look at the numerator. So if I put in 0, I get negative times a negative, which is positive, which means I am increasing. If I put in 3, I'll have a negative times a positive, which is negative, which means I am decreasing. If I put in 5, I'll have a negative times a positive. This is a negative, which means I am decreasing. And then if I put in 7, I'll have a positive times a positive, positive, so it's increasing. Then I note that there must be relative maxes and mins here. There's a relative max at x equals 2. And then there's a relative min at x equals 6. I'm not sure what those values are. You can just put them back into the original function to get that answer. So if I put 2 into this thing, I would get 4. So the point would be x equals 2, comma, 4 minus 12 plus 12. So it's 4 all over negative 2, which would equal, or would tell us it's at the point 2, comma, negative 2. And then the relative min is at 6. So putting 6 in here, I get 36 minus 36 is 0. So 12 all over 2, which is 6. Okay, so its ordered pair is 6, comma 6. And we could plot those on top of everything else. So let's do that. The max, the relative max is at 1, 2, comma, negative 2. So right here. And then the relative min, 4, 5, 6, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 6. Okay. Okay. So getting a lot of information here. Let's get the second derivative going. We could try x is 0 again, and then x is 5. Let's find the second derivative back in the notes. This is the second derivative, so if you plug in 0, you get 8 over negative 4 cubed. Negative 4 cubed is negative 64, so it's positive over negative. It's negative, it's concave down. If you plug in 5, you'll get a positive over positive, so that'll be concave up. Okay, and now we should be able to put everything together. There's one last thing. There's this weird slant asymptote at x equals, y equals x minus 2. If you recall, we had this slant asymptote. So I want to plot it. So I'll just note slant asymptote y equals x minus 2. To plot this thing, the slope is the thing in front of x, which is 1. And then the y-intercept is at 0, negative 2. Okay. So that just tells you the end behavior of the graph. So let's maybe put it in a different color. I'll put it in green. So 0, negative 2, and then the slope up 1 over 1, up 1 over 1 is going to be right about there. And the graph will conform to this asymptote as x goes to negative infinity and x goes to positive infinity. Okay, so in this region I am below. I am also concave down, and I am increasing all the way to 2, and then it starts decreasing. Okay, so it's concave down, increasing all the way to 2, and then decreasing like that. Okay, and it should get closer to the green line. I screwed up and kind of made it go a little down. It should be going like this, closer to the green line. But it's concave down, so there shouldn't be any sort of bumps. It's concave down, like that. Okay. It could possibly go through that slant asymptote. I have not gone through that kind of detailed analysis yet, though. So we'll just sketch it like that. Then the upper part, you know, we're above, past this asymptote, we're always above the x-axis. It's first decreasing and then increasing once it hits this minimum value of 6, and it's concave up, and it'll conform to this green line. Okay? So it's above, it's decreasing, and then it'll hit this minimum value of 6, 6, and then it'll be increasing, and I suppose it'll do something like that. Okay, so it's still kind of a sketch in some ways, but it's a pretty detailed sketch, especially with the concavity thrown in. Okay, so let's look at number 25, which will be graphing a logistic equation, which you see these things in differential equations. We saw a little of a logistic equation in the learning theory problem. If you look at my last video lecture. Okay, so let's look at 25. Right, so this is g of t equals 10 all over 1 plus 4e to the negative t. Okay, and for the sake of sanity, I'll rewrite it as 10 times 1 plus 4e to the negative t to the negative 1. Okay. Okay, so first off, the domain. The domain for this thing is all real numbers except where the denominator is equal to 0. And the denominator won't equal 0. So you take a look at it here. Solving this, you get 4e to the negative t equals negative 1. Exponentials are never going to be negative. Okay? You can't raise a number like 2 to some power and magically make it negative. Okay? So this will not work. So the domain is all real numbers. Okay. Secondly, we're going after the x and y intercepts, x-intercept, y-intercept, and then vertical asymptotes. So the x-intercept is there, y is 0, so 0 equals 10 all over 1 plus 4e to the negative t. In other words, you're setting the numerator equal to 0, and of course that has no solutions, so there's no x-intercept. For the y-intercept, you let x equal 0, so we'll have y equaling 10 all over 1 plus 4e to the 0. Anything to the 0 power except 0 is just 1, so I have 1 plus 4. That'll be 10 all over 5, which is, of course, just 2. So my y-intercept is at 0, 2. There is no vertical asymptote because the denominator never equaled 0. Okay, so I'll just note that. The vertical asymptote, none. Okay, thirdly then, horizontal asymptotes. So I want to take a look at the limit of this thing as x goes to positive and negative infinity. This was a special limit type, so the limit of this part is 10, the limit of this part is 1, the limit of this, and it's really t as time goes to infinity. The limit as t goes to infinity of this thing will just be 0, this portion of it, because you'll have 1 all over e to the 10, 1 over e to the 100. The limit of this part as t goes to infinity is 0. Okay, so the limit of the overall thing is just 10 over 1 plus 0, in other words, 10 over 1, which is 10. In the other direction, we get a different asymptote. So as t goes to negative infinity, 10 all over 1 plus 4e to the negative t, the limit of this little part here, this exponential part, 4e to the negative t, as t goes to negative infinity this time, you're plugging in, well, what does this graph even look like? Maybe that's an easier way to think of it. E to the negative t is just a reflection of e to the t about the line y equals, or x equals 0. This is e to the negative t. So as t goes to negative infinity, e to the negative t is just getting bigger and bigger and bigger and bigger. It's going to infinity. Okay. So what do you have? Well, you have L all over infinity. And we said earlier in the class, limits of this type always go to 0. So actually, in the negative direction, we have a horizontal asymptote, y equals 0. Okay, then we need derivatives. So fourthly, I guess, y prime equals, and I'll use this version here to figure out this derivative, negative 10 times 1 plus 4e to the negative t times, raised to not the negative 2, times the derivative of the innards. So that would be 4e to the negative t times negative 1. Okay, so this will clean up a little bit. It'll look like the following. 10 all over 1 plus 4e to the negative t, which is just g of t, y, times 4e to the t, 4e to the negative t all over 1 plus 4e to the negative t. Okay, and I do this in a kind of to avoid having to get that second derivative, okay? Because if you look at this guy, it's really just y times something. Okay? And what is this something? Well, if you do a bit of fancy footwork, you go plus or minus 1 up on top, you can butterfly the thing, and it'll end up being 1 then minus 1 all over 1 plus 4e to the negative t, which is the same as, if you go through the math, it will be the same as y all over 10, believe it or not. Okay, so y prime is kind of, they'll say, proportional to itself in this weird sort of way. Okay, so where does this equal 0? Well, in order to answer that question, we really sort of have to work with this, I guess, and figure that out. So maybe this is a little too much at this point. Yeah, let's skip that and just work with this thing. So where is that thing equal to 0? You take the numerator, set it equal to 0. 4e to the negative t times 10 equals 0. That'll never equal 0, right? Exponentials will never output a 0, so this won't ever work. This has no solutions. The only hope is maybe it's not defined somewhere. So if you take the denominator, which is just this factor times this factor, in other words, 1 plus 4e to the negative t squared, and set it equal to 0, maybe then there's a critical value, right? Square root on both sides, 1 plus 4e to the negative t is 0. No, it's not going to work, right? Because you'll never get negative value out of this exponential. So again, there's no solutions. Ugh. Okay, so no critical numbers. What does that mean to us? That means it's going to always be increasing or always decreasing on all values of its domain. All right, let's look at 5, and this is where I was kind of hoping just to work with this secondary form of the derivative, kind of trying to avoid having to take the derivative of this mess here. You know, I guess, sure, let's go ahead and take the derivative of the mess. No, on second thought, no, let's not. Let's take the derivative of this thing, okay? And we could do that implicitly. So if y prime equals y times 1 minus y over 10, we could distribute this and say that's the same as y minus y squared over 10. And then y double prime is going to equal the derivative of this implicitly. So the derivative of y is 1 times y prime, and then minus the derivative of y squared over 10 is 2y all over 10 times y prime. In other words, y all over 5 times y prime. So this will equal y prime times 1 minus y all over 5. And we already kind of know where y prime is equal to 0. It's not, right? So we can kind of exclude that factoid and throw that out the back door, and just look at this part of it. So where is y over 5 equal to 1? In other words, where is y equal to just plain old 5? If we go up to our original function for y, this is equal to 5. You kind of know that. You've done a little bit of work. I think it's well, maybe you don't. Well, we can solve this, right? Let's take it and solve it. So y is 5 when t is what? So 1 plus 4e to the negative t, and then just solve for t, and that should give us our inflection points. So I have 1 plus 4e to the negative t equals 2. 4e to the negative t is equal to 2 minus 1 is 1. So e to the negative t, I'm looking for where that's 1/4. It's a logarithmic equation. Take logs on both sides. You get negative t equals ln of 1/4. multiply both sides by -1, and you're looking at where t is equal to ln4. Okay. So yeah, it has kind of an inflection point here. Let's start putting all this business together, shall we? All right, so here I go. Did I find, I didn't, yeah, I found the horizontal asymptotes at 0 and 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's a horizontal asymptote. I need to worry about my f of, in this case, they're calling it g of t. So g of t, I need a number line for g prime of t, and then another one for g double prime of t. Okay, g of t is equal to its x-intercept. Well, there wasn't one, right? There's also no vertical asymptote, so we don't plot anything. And for the number line, it's always going to be increase. It's always going to be above or always below the x-axis. Okay, so we just need one test value to determine that. For g prime of t, there were no critical numbers, so it's always either going to be increasing or decreasing. For g double prime of t, there's the ln of 4 as our critical number. And so ln of 4, I'm not sure exactly what that number is, so like 1.38. Okay, so 1.38-ish in here somewhere. It's always said don't plot the other points. 1.38 is what I'm calling ln of 4. Okay, so you need to go through, get your test values, signs, and conclusions. So test value, signs, conclusions, test value, signs, conclusions. Okay. So you do any test value, try x is 0 here, or t is 0. Plugging that into our original function, when t is 0, we already kind of know that'll be 10 over 1 plus 4, 10 over 5, which is 2. Okay, so that's our also our y-intercept. We might as well go ahead and plug that in there. But anyways, it'll be positive. In other words, it's always going to be above the x-axis. Okay. Again, let's use t as 0. If you plug that into the derivative formula, which is this thing, you'll get 10 times 4e to the 0, so you get 40, which is positive, all over 1 plus 4 times 1 plus 4. That'll be a positive as well. So it's positive over positive, so it's positive. In other words, it's always increasing on its domain. Okay. Finally, then, on either side of 1.38, we could try t as 0, and then t is, I don't know, ln of 8. And our function, our second derivative, so I'm really getting just, it sucks I didn't get the second derivative, let's put it that way. I should have, in class, I'll do the second derivative, so don't worry about this, but if I had the second derivative, I would plug it into there, and I would find that it's positive and concave up on that interval, and then negative and concave down on this interval. And then I could start putting things together. Okay. So at 1.38, it's going to go from concave up to concave down. I have a horizontal asymptote in this direction, y equals 0. So it's going to be down here, and then it's going up, concave up until about 1.38-ish, and then it will go concave down and get really, really close to y equals 10, its other asymptote, and it's concave down past this point, 1.38. But it's always increasing. It's always above the x-axis. And this guy we'll call eventually the logistic equation. So it's a way of modeling population growth. We saw it before for modeling learning curves. Okay, great. Thanks for watching.